The paper discusses a novel multi-computing engine (CE)-based FPGA accelerator for lightweight convolutional neural networks (LWCNNs) with balanced data flow. It aims to tackle issues such as high on-chip, off-chip memory overhead and low computational efficiency in existing LWCNN accelerators. The proposed accelerator uses a streaming architecture with hybrid CEs, which minimizes off-chip memory access while maintaining a low cost of on-chip buffer size. A balanced dataflow strategy is introduced to enhance computational efficiency by improving efficient resource mapping and mitigating data congestion. Additionally, a resource-aware memory and parallelism allocation methodology is proposed to achieve better performance and scalability. The proposed accelerator is evaluated on Xilinx ZC706 platform using MobileNet v2 and ShuffleNet v2, demonstrating significant improvements in performance and MAC efficiency compared to current LWCNN accelerators. Here is a combined summary of pages 3 and 4 of the research paper. The authors analyze the memory access patterns and computational loads of lightweight convolutional neural networks, LWCNNs, and identify the need for an optimized architecture that minimizes memory access costs while ensuring high computational efficiency. They calculate the ratios of deepwise separable convolution, DSC, and shortcut connection block, SCB, to standard convolution, STC, in terms of multiply accumulate, MAC, operations and feature map, FM, memory access, highlighting the significant reduction in operations by DSC and SCB compared to STC but at the cost of increased FM access. The authors also discuss the distribution of FMs and weights in LWCNNs, noting that the number of parameters and weights varies from layer to layer, with shallow layers generating larger FMs and consuming more parameters, while deep layers produce fewer FMs but require massive parameters. They illustrate this phenomenon using MobileNet v2 and ShuffleNet v2, showing that different FM and weight distributions led to distinct memory footprints and data reuse rates in each layer. The authors review related works on LWCNN accelerators, including those that perform all kinds of convolutions within a unified computational element, CE, those that develop dedicated CEs for DWC processing, and those that employ a multi-CE architecture for LWCNNs. However, they identify limitations in these approaches, such as low computational efficiency, high power consumption, and suboptimal memory footprint. To address these limitations, the authors propose a streaming architecture with hybrid CEs for memory optimization and a balanced dataflow strategy for computing optimization. The architecture consists of two types of CEs: feature reuse computing engines, FRCEs, for shallow layers, and weight reuse computing engines, WRCEs, for deep layers. FRCEs eliminate off-chip memory access by storing all weight data on chip, while WRCEs minimize external memory traffic for weight data through a fully reused weight scheme. The authors claim that their proposed accelerator reduces on-chip and off-chip memory utilization while enabling high computational efficiency for LWCNN acceleration. The research discusses novel approaches to reduce on-chip memory occupation and off-chip memory traffic in streaming architectures. It proposes two types of processing elements: CEs, FRCEs and WRCEs, each with distinct data reuse schemes. FRCEs focus on fully reused feature maps to minimize off-chip memory access, while WRCEs emphasize fully reused weights for deep layers. The fully reused feature map scheme reduces the line buffer size by caching convolution windows, allowing for a higher weight reuse rate. This approach saves one line of buffer size compared to the line-based reuse scheme and decreases computation delay. The design targets shallow layers for FRCEs and deep layers for WRCEs to achieve optimal performance. The paper also introduces a ping-pong structure-based global FM buffer for storing FM data entirely, reducing off-chip memory traffic in deep layers. The comparison between FRCE and WRCE is summarized in Table I, highlighting their differences in reuse schemes, weight storage, and suitability for different layers. The layer-specific CE design is adaptive, ensuring high bandwidth while minimizing logic resource consumption. This includes a handshake mechanism for synchronization and parallelism tuning to match computing bandwidth. The research concludes by emphasizing the efficiency of the proposed schemes in reducing memory occupation and traffic, making them suitable for high-performance streaming architectures. The proposed memory-optimized streaming architecture for LWCNNs aims to enhance computing efficiency by addressing the limitations of current streaming accelerators. The architecture is based on a novel fine-grained parallel mechanism and a data flow-oriented line buffer scheme. The fine-grained parallel mechanism extends the parallel space in each parallel dimension to achieve optimal overall resource allocation. This approach allows for more available parallelism, reducing overall location and alleviating the staircase effect in bottleneck layers. Consequently, it promotes the overall throughput with the same hardware resources. The data flow-oriented line buffer scheme addresses data congestion issues caused by inefficient padding implementation and a mismatch between buffer organization and convolutional stride. Instead of writing padding data directly into the line buffer, the padding operation is performed by the address controller within the CE while pixels are sent to the PE array. This approach prevents data congestion in upstream data and increases input bandwidth indirectly, eliminating window bubbles during image switching. For convolution layers with large strides, an additional line buffer is allocated to eliminate window bubbles caused by the mismatch between limited buffer space and required data scope. The proposed architecture significantly enhances the computing efficiency of STC and DWC layers with diverse padding locations and strides. By optimizing the padding generator and additional buffer space, the architecture ensures sufficient bandwidth supply and minimizes idle hardware resources. Overall, the memory-optimized streaming architecture for LWCNNs offers a balanced dataflow strategy that improves the computing efficiency of streaming accelerators. In the proposed research paper, the authors present a resource-aware memory and parallelism allocation methodology for optimizing the performance and compatibility of a streaming neural network accelerator. The methodology is decomposed into two parts: a balanced memory allocation algorithm to identify the group boundary that minimizes off-chip memory access while meeting on-chip memory constraints, and a dynamic parallelism tuning algorithm to distribute processing elements, PEs, for each layer to achieve maximum throughput with a certain number of digital signal processors, DSPs. The balanced memory allocation algorithm iteratively determines the number of FRCEs, fused reconfigurable computing elements, based on the memory evaluation model. It aims to find the configuration that uses the smallest SRAM size by incrementally increasing the number of FRCEs layer by layer until reaching a specific layer where the SRAM consumption with FRCEs exceeds that with WRCEs, weight reuse computing elements. The algorithm then continues to advance the boundary layer based on the results of the first iteration until the utilized SRAM size exceeds the threshold. The dynamic parallelism tuning algorithm adjusts the parallelism of each layer to balance the computing time among all CEs, computing elements. It initially configures the parallelism of each layer to 1 and then searches for all bottleneck layers to increase fine-grained parallelism. The increments in parallelism have different priorities depending on the CE type. The iteration continues until the number of DSPs reaches the resource constraint. The authors evaluate the effectiveness and generality of the proposed architecture using 4 representative LWCNNs, lightweight convolutional neural networks, as benchmarks for memory and computing simulation. They also implement Mobile Net v2 and Shuffle Net v2 on the Xilinx ZC706 board to further validate the proposed architecture. The results show that the proposed design significantly reduces the on-chip memory size and off-chip memory access compared to other streaming architectures. The research paper discusses the design and evaluation of a novel streaming architecture for lightweight convolutional neural networks, LWCNNs. It presents a hybrid data reuse scheme, reducing SRAM consumption by 81.37% compared to existing schemes. The proposed architecture also achieves an average FM access reduction of 98.07% and 96.69% compared to the unified CE and separated CE architectures, respectively. The evaluation process focuses on the theoretical throughput and scalability of the FGPM compared to baseline schemes. The results demonstrate a significant improvement in MAC efficiency, ranging from 93.06% to 95.68% across various MAC configurations, representing a 6.46% to 31.29% improvement over the baseline. The paper also provides detailed implementation examples for Mobile Net v2 and Shuffle Net v2 on the ZC706 platform, highlighting the effectiveness of the balanced dataflow strategy and the FGPM in enhancing computational efficiency and reducing resource utilization. The comparisons with state-of-the-art LWCNN accelerators show that the proposed design outperforms several existing solutions in terms of performance and computing efficiency. This research paper presents an efficient and scalable lightweight CNN, LWCNN, accelerator, accompanied by various memory and computing optimizations. The proposed design achieves state-of-the-art performance, with a throughput of up to 2092.4 fps and a remarkable peak efficiency, PE, of up to 94.58%. The accelerator's hybrid CE architecture eliminates off-chip access for intermediate feature maps, thereby reducing memory occupation and improving computational efficiency. The balanced dataflow strategy optimizes resource allocation and on-chip bandwidth, resulting in high MAC efficiency. Additionally, the proposed design realizes a competitive DSP utilization of around 95% due to the scalable architecture and dynamic parallelism tuning algorithm. The paper also presents a comprehensive comparison of the proposed accelerator with previous Mobile Net v2 accelerators in terms of performance, memory occupation, and energy efficiency. The results demonstrate that the proposed design outperforms previous works, achieving higher throughput and better PE while reducing off-chip memory traffic and SRAM size. The authors also provide an extensive list of references, citing various works related to CNN acceleration, FPGA-based designs, and optimization techniques for deep neural networks. The references cover a range of topics, including CNN processor architectures, FPGA-based overlay processors, and efficient dataflow accelerators for LWCNNs. In conclusion, this research paper presents a significant contribution to the field of LWCNN acceleration, offering a highly efficient and scalable design that achieves state-of-the-art performance and energy efficiency. The proposed optimizations and techniques can be applied to various CNN architectures and FPGA-based designs, making it a valuable resource for researchers and practitioners in the field.